We are going to start off on page 37 in your exponential unit packet. And we're actually going to talk about the inverse of an exponential function for today. So we talked about inverse functions. The inverse of a function would mean I switch x and y, switch the input and the output. So every function that we could look at, and we've looked at linear functions, we've looked at quadratic functions, cube root functions. We can find the inverse of all of those types of functions. We can also find the inverse of exponential functions. The inverse of an exponential function is what we call a logarithmic function. Okay? So we've seen a little bit of logs so far. So we know logs have this format to them. And we can convert them to an exponential format if we want. So the base for my log becomes the base for my exponent. Whatever is the argument of my log, that's what this guy's called right here, is what my exponent is equal to. And then whatever my log is equal to is actually the exponent for my exponential equation. We call, again, b the base. And our base can be any number greater than 0, so we're not dealing with negative bases for logs. When b is 10, when the base for my log is 10, we call this a common log, so we're going to see that a little bit later on. If you have a common log, you actually don't have to write the base. So if you ever see a log and there's nothing written here, the base is 10. We can also have a base of e. E is a number that is bigger than 0, so it's fair game as the base for a log. You could also, I suppose, have a base of pi if you wanted. But if your base for your log is e, then we call this a natural log, and we use this notation. So if you have ln instead of log, that ln tells you you have a natural log, so it would be a log with a base of e. Now, recall again that for inverse functions, we're going to switch the input and the output values. That will come into play when we start looking at graphing these log functions. But before we get there, I want to take a little bit deeper look at this idea that exponentials and logs are inverses of one another. So remember, to find an inverse function, I start by switching x and y, and then I want to get y by itself. So if I want to find the inverse of this function here for a, I'm going to start by switching x and y. So this would be log base 3 of y equals x. And now, in order to get y by itself, I'm going to have to rewrite this in its exponential form. So this would be 3 to the x equals y. So the inverse of my log function gives me something exponential. For b, same idea. I'm going to start by switching x and y. Log of y equals x. And now, in order to get y by itself, I'm going to have to rewrite this. Now, I don't see a base for my log here. That means that this is a common log, and the base is 10. So I would have 10 to the x equals y. And now y is by itself, so I don't have anything else to do with that function. This is the inverse. For c, again, I'm going to start by switching x and y. X equals the natural log of y plus 1. Since this is all in parentheses, I'm not going to touch anything inside of those parentheses. That is all the argument for my log, and I don't want to touch it. Instead, what I want to do to get y by itself is to start by rewriting this in its exponential format. So here, that ln, remember, is what we call the natural log, so its base is e. So as I rewrite this, the base for my exponent will be e. I'll have e to the x equals y plus 1. Now for this problem, I do have one more step. I want y by itself, so I need to subtract 1 from both sides. I would get e to the x minus 1 equals y. And there's my inverse function. Now, on top here, this top row of examples, we started with logs, and our inverse functions are all exponential functions. For d, I've got an exponential function, and e, same, I've got an exponential function. I want to start by switching x and y, so x equals 3 to the y plus 1. And in order to get y by itself, to get y out of the exponent, I'm going to have to rewrite this in log form. So this would be log base 3 of x equals y plus 1. On this problem, again, just like C, I've got one more step to get y by itself. I'm going to subtract 1 from both sides. I want you to keep in mind for this problem that I'm not putting parentheses around the x minus 1. The minus 1 is after I take the log. It is not part of the argument, so I do not want to group it with the argument. I would do the log first and then subtract 1. Now for e, same idea. I'm going to start by switching x and y. So x equals 1/2, and this 1/2 really should probably be in parentheses, to the y minus 2. And now I'm going to rewrite this in its log format. So log base 1/2 of x equals y minus 2. And now one more step to get y by itself. And I would get log base of 1/2 of x. And if you want, since x is the argument, you can put just x in parentheses. I could do that over here too, just to be super crystal clear. And then plus 2 equals y. So we talked about how if we started with a log function, like those top 3 examples, I ended with an exponential function. I also want you to notice the examples where we started with an exponential function, we are ending with a log. You're ending with a logarithmic function. Okay? So exponential and log functions are inverse functions. Now we talked about graphing exponential functions. So we're also going to talk about graphing, logarithmic functions. So let's start with a little refresh on graphing an exponential function. So we would start with a key point based on our function. We'd actually start with the asymptote. If I back up here a little bit, my asymptote would be at 0, y equals 0. So I'm going to put that right here along the x-axis. Remember, for exponential functions, we have a horizontal asymptote. That will be important in just a second. And then I would look for my value in front of the thing with the exponent. In this case, since I don't see it, it would be 1. That tells me how far to go up from my asymptote. I don't see anything that gives me left or right transformation, so I'm going to go up 1, and that's it. That would be my key point, 0, 1, which would also happen to be my y-intercept in this case. And now if I wanted to, I could graph this with a table or by looking at using that growth factor to find more points. As I move forward, since my base for my exponent is 2, this means I would double the distance to my asymptote. So here my distance is 1 as I move forward. Now that distance is 2. If I move forward again, double the distance to the asymptote. So it's 2, double that to 4. I could go back this way as well, cut it in half, reverse that operation, and I would get a few points. The other thing that we could do is just pick some values for x to plug in. So I know I have the point 0, 1. We could also plug in -1 for x, or 1, or 2. So if I plug in -1, this would be 2 to the negative first power. That would flip us to 1 over 2. 2 to the first power would be 2, and then 2 squared would be 4. We won't take a lot of time to point this out, but I would like us to acknowledge here where we've got a pretty easy function that my key point should also make sense for my function. So if I did 2 to the 0 power, anything to the 0 power is just 1. So my x and y pair should make sense for my function for these exponential graphs. And then anytime we graph an exponential function, I've asked you for at least 3 points, and we have that here. So I'm going to go ahead and connect them and throw my arrows on the end. So there's my exponential function. Now let's take a look at a log. This is actually the inverse of this exponential function. If I were to switch x and y here, so x equals 2 to the y, I would have to rewrite this. This would be log base 2 of x equals y. That's what I have here, log base 2 of x. This is the inverse of our super basic exponential function. So my points here, my x and y values will be swapped. When x is 1/2, y is -1. When x is 1, y is 0. Again, I'm just reversing the points for my exponential graph. When x is 2, y is 1. When x is 4, y is 2. So 1/2, -1, 1, 0, 2, 1, 2, 3, 4, 2, So as I get closer to the y-axis now, my points will get smaller and smaller and smaller. And I'll trend out this way as I get bigger and bigger. If I had more points here that I could transfer over, that's the pattern I would see. It sort of looks like I've taken my exponential graph and sort of flipped it this way. Okay, so I get something that looks like this. That key point that we had from here is flipped, right? So if we talked about a key point on this, it would be the flip of our key point from that exponential function. This time our asymptote is going to be vertical. Instead of y equals something, it's going to be a vertical line. So we'll get x equals, in this case, 0. And then our x-intercept is that other important point that we'll talk about. We know for an exponential function, we should always cross the y-axis. We may not always cross the x-axis. That's flipped for our log functions. Well, we should always cross the x-axis. We may not always cross the y-axis. So our x-intercept here would be 1, 0. As we graph some more log functions on the next page, I'm going to show you a strategy sort of based off of this idea that logs are inverse exponential functions, so that we can rewrite logs as exponential functions. So let's go ahead and turn the page to page 38. And let's take a look at a few more graphs here. So the same as we would look at our function first to determine where our asymptote is. And our asymptote for exponential functions was at the end because our asymptote moved up or down. It was a y equals thing. We're going to start by looking for our asymptote with these log functions too. But this time, since our asymptote is vertical and it's defined as x equals something, we're going to look for any shifts left or right. So we're going to look in with x. Okay, if it's in parentheses with x, that tells me where my asymptote is moved to. So this tells me that I would have a shift to the left 2 places. So my asymptote would be at x equals -2. It is important to put the x equals there. We are talking about a line, so I need to describe it as a line. And just how when I graphed exponential functions, I started by graphing the asymptote, I'm going to do the same thing here. Now here's where I'm going to differ. For logs, I personally find it a lot easier to graph a log when it's written like an exponential function. It is not the easiest thing in the world to pick values for x to plug into a log function that will give me nice y values. Sometimes I may be picking values for x that give me kind of messy y values. Now that's not necessarily a bad thing if you can use your calculator to help you simplify the log base 2 of 3 or the log base 2 of whatever you happen to plug in for x when this simplifies. If you can use your calculator to help you, then you can get whatever values you want, and it kind of doesn't matter. But if we're graphing these without a calculator, which I'm going to ask you to do, then it's important that I pick values that are going to give me some decent points and not be too terrible to figure out on my own. So what I'm going to do here is actually rewrite this in its exponential form. I'm not going to get the full inverse. I'm just going to rewrite. So I'm not switching x and y. I'm just rewriting. So this would be 2 to the y equals x plus 2. So I changed this to its exponential form. All I did was rewrite 2 to the y equals x plus 2. And now what I'm going to do is a little tricky. Instead of picking values for x to plug in, because again, that would be complicated. 2 to what power gives me this number? Well, I could be really selective about what I pick for x so that I get stuff that's going to be powers of 2 to make it easy to find y. But the even easier version is just to pick values for y. So we're used to picking values for x. Here, I'm going to throw that out the window and tell you to pick values for y. So -1 is not a terrible exponent to evaluate. 0 is not a terrible exponent to evaluate. Neither is 2 to the first or 2 squared. So I'm picking values for y, and I'm going to plug them in here to see what I should get for x. So if I plug in -1, I know that that means I would have 1 over 2. So x plus 2 would give me a half. What was x, right? That's what I'm asking here. X plus 2 equals a half. What was x? Well, x would have to be negative 1.5. That's the only thing I could add to 2 and get half. If I plug in 0 for my exponent, 2 to the 0 would be 1. So x plus 2 equals 1. What did x have to be? Negative 1. 2 to the first would be 2. So x plus 2 equals 2, right? This is that 2. So what did x have to be? 0. If I plug in 2 for y, that would be 2 squared, which is 4. So x plus 2 equals 4. X had to be 2. Now, these are my points for my function. I don't need to swap my table. I have the table for my function. I'm going to go ahead and plot these points. So negative 1.5, negative 1, negative 1 comma 0, 0 comma 1, and 2 comma 2. This would be what I would identify as my key point if I were looking at my exponential function, right? Shifted. We're not going to talk so much about key points for our log functions, though, since we're going to probably pick something close to the same y values each time. So there's my logarithmic graph. Now let's talk about domain and range for a second. Remember, domain refers to those x values, range refers to the y values. So my domain, my x values, it's okay to plug in. This is going to be limited by my asymptote. My x values will have to be greater than negative 2. So I could write this a couple different ways. I could say, if I use interval notation, my x values, my domain would be 2, negative 2 to infinity, parentheses, because I can't actually have infinity and I can't actually have negative 2 because of the asymptote. I could also represent this as x is greater than negative 2. For my range, this would be my y values. Now we're going to go forever down. We're also going to slowly creep forever up. So my range here would be all real numbers from negative infinity to positive infinity. Or if I wanted that inequality notation, negative infinity is less than y is less than positive infinity. Let's take a look at another graph now. For b, 2 times log base 2 of x minus 3. So again, I want to rewrite this in its exponential format. Before I can do that, though, I have to get the log by itself. So I'm going to start by adding this 3 over to the other side. So I know I'm working at the very tippy top of my paper here. I would have y plus 3 equals 2 log base 2 of x. And now, again, I want the log by itself. I can't have this 2 hanging out here. So I'm going to divide both sides by 2. And I get y plus 3 over 2, the whole thing over 2, equals log base 2 of x. Now I've got the log by itself. So I'm going to rewrite this in its exponential format. This would be 2 to the y plus 3 over 2 power equals x. Now that is a messy exponent, but that's okay because what we're going to do, again, is pick values to plug in for y. So it's okay if the exponent's a little gross because I get to pick what I plug in here. Now I'm going to be very selective about the values that I choose to plug in for y. I'm going to plug in something that makes the exponent simplify to a nice number. So let's say I plug in 1. If I were to plug in a 1 here, 1 plus 3 gives me 4. That's an even number, so I could divide it by 2. What I'm trying to avoid are having super gross exponents to have to evaluate. This is already kind of a yucky exponent to have to deal with, so I don't want to make my work any harder. So I'm going to pick 1's not so terrible. If I plugged in negative 3, the top here would be 0. That's easy to work with. I could also plug in, probably don't want negative 2 because negative 2 plus 3 is 1, and that would give me a half for my exponent. I don't know how to simplify the square root of 2 without a calculator, so I'm going to leave that one. But if I plugged in, let's see, negative 1, that wouldn't be too bad. I don't want to plug in 0 because then my exponent would be 3 over 2. Again, 1 is not too bad. 2 I would avoid since I'd have 5 over 2. If I wanted to go more than 3 points, I might plug in 3, right? I'm plugging in stuff so that the top's going to be even. So when I do this, I would get 2 to the negative 3 plus 3 over 2 power. Now this would be 0 over 2, which would just be 0 for my exponent. Anything to the 0 power is 1. Now I'm going to plug in negative 1. So this would be 2 to the negative 1 plus 3 over 2. Negative 1 plus 3 would be 2. 2 over 2 is 1. So this is 2 to the first power, which is 2. And then 1. This would be 2 to the 1 plus 3 over 2. I know this is a lot. 1 plus 3 is 4. 4 divided by 2 is 2. So I get 2 to the second power. 2 squared is 4. Okay. This could have been a lot worse if I had picked anything for y. You can pick anything for y, but if you're selective, this gives you a little bit nicer numbers to graph. So I'm gonna plot my asymptote first. I don't see anything in parentheses with x. That means my asymptote remains at x equals 0. And now as I plot my points, I've got 1 comma negative 3, 1, 1, 2, 3. I've got 2 comma negative 1. And then I've got 4, 4 comma 1. There's my log. There's my logarithmic graph. My domain again is limited by my asymptote. So I'll have to have x values that are greater than 0. My range is not limited. I'm going to go down forever. I'm going to go up forever. So my range would be anything from negative infinity to positive infinity. Let's take a look at another one, a little bit easier one for C. So my function is y equals log base 5 of x. I'm going to rewrite this in its exponential form. That would be 5 to the y equals x. So again, I'm going to pick values to plug in for y and see what I get for x. So I'm going to pick negative 1, 5 to the negative first power. Shouldn't be terrible. 0 as an exponent, not terrible. We'll plug in 1 and we'll plug in 2. So if I do 5 to the negative first power, I would flip this and get 1 over 5. That'll be a little tricky to graph, but not terrible. 5 to the 0 power would be 1. 5 to the first power is 5. And then 5 to the second power is 25. This last point will be off my graph. That's okay. So I'm going to go ahead and put my asymptote down on my graph. I'm not shifting left or right any, so my asymptote will stay at x equals 0. And now I'm going to plot my points. When x is 1/5, y is negative 1. Really close to our asymptote there. We have the point 1 comma 0. 1, 2, 3, 4, 5 comma 1. And then our last point here, 25 comma 2, would be way off our graph, so we won't worry about that one. We do have 3 decent points on our graph here. My domain, again, limited by my asymptote. So this would be from 0 to infinity. I'm using a parenthesis here because I cannot actually have 0 as an x value due to my asymptote. My range, though, is not limited. We're going to go down forever. We're going to very slowly creep up forever. So this would be from negative infinity to positive infinity. Last example for today, D. I've got log base 1/2 of x. There are a couple things I want to show you here. First, let's treat this just like we've done every other problem. So this would be 1/2 to the y equals x. And now I'm going to pick some values that make sense for y. Remember, if I do a negative exponent, that's going to flip this. So I'm actually going to pick some more negative values. So I'm going to do -2 and -1, since that will flip my fraction to be a whole number. And we'll do 0 and we'll do +1. So 1/2 to the negative second power would be 2 squared, which is 4. 1/2 to the negative first power would be just 2 to the first, which is 2. 1/2 to the 0 power would just be 1. And then 1/2 to the first power would just be 1/2. I'm not moving left or right any, so my asymptote stays right on the y-axis, and it will be x equals 0. And now let's plot our points. So this would be 1, 2, 3, 4 to the negative 2, 2, comma, negative 1, 1, comma, 0, and a half, comma, 1. So notice we get sort of an upside down log here. This one's kind of flipped from the other problems that we've had so far. Okay, normally they go like this. This one's going the opposite. Okay. Domain and range I still evaluate the same way. Domain still bounded by that asymptote. So this would be anything from 0 to infinity. Range not bounded, so negative infinity to positive infinity. This would be the graph of log base 1/2 of x. Now, if I wanted to, and this will make the flip part make more sense, if I wanted to, there is a special property of logs that says if your base is a fraction, you can actually rewrite it. So instead of log base 1/2 of x, we could rewrite that as negative log base 2 of x. This is another way I could represent that. Now, if I wanted to use this alternate form instead, y equals negative log base 2 of x. If I were to rewrite this, I'd have to start by getting rid of that negative. So I would get negative y equals log base 2 of x, and then rewriting, so I would get 2 to the negative y equals x. Now I want you to notice 2 to the negative y means whatever I plug in for that exponent, the sign is going to change. So if I were to plug in negative 2, this would be 2 to the negative 2. So that'd be 2 to the positive 2, okay? Or 2 squared, which would be 4. So if I plugged in negative 2 to this other function, I would get 4. If I were to plug in negative 1 here, that would be 2 to the negative 1, or 2 to the positive 1, which would be 2. 2 to the first, right? It's 2. So I would get the same points here. So you can use this special property or not. We could still clearly evaluate it if it's a fraction, but if the fraction gives you trouble, there's an alternative here with that special log property. What I do think is helpful though, is seeing that negative, right? That negative in front. We're used to our transformations where that negative in front tells us that we flip our graph over the x-axis. So this negative in front does help explain why our log graph seems like it's going the opposite direction. We would expect it to come up like this, but it's coming down like this. Okay, it's because of that special log property that if we have a fractional base for our log, that actually means that we could rewrite it with a negative coefficient. So inverse of exponential functions are logs. We looked at their graphs. We're going to continue to do a little more work with this idea of exponentials and logs being tied together. But that's it for today.